We shall commence this module by discussing about linear programming in brief. Linear programming can be defined as matrix algebra's application that is formulated to have a solution of problems of wider class, and linear equations are used to represent them. A linear equation, that is, equation which is algebraic, the variable or variables, quantities of which are first powered only and the graph of which is made, will give a straight line. These problems are attributed objective function which is to be minimized or maximized depending upon the need of the problem, and this is subject to a number of constraints. Both constraint and the objective function are represented with respect to linear equality or inequality. In a typical situation, the objective function would be given for profit maximization, example margins, or cost minimization, like variable costs. The following assumptions need to be satisfied to justify the use of linear programming. First, linearity. Functions such as prices, cost, and technical needs must follow linearity function. Second, certainty. Parameters are expected to be known with certainty. Third, non-negativity. Decision variables, if turn out to be negative, will not be acceptable. Two approaches are commonly used to solve LPP problems. First, graphical method, and second is the simplex method. In this module, we shall focus on graphical method. The graphical method is limited to linear programming problems in solving two decision variables and a limited number of constraints due to the difficulty of graphing and evaluating more than two decision variables. This restriction severely limits the use of the graphical method for real-world problems. The graphical method is presented first here. However, because it is simple and easy to understand and it is a very good learning tool, after studying this module, you shall be able to know about linear programming, learn how to formulate linear programming problem, and learn how to solve linear programming problems with the help of graphics. Let us first discuss the steps involved in solving a linear programming problem graphically. The steps involved in solving a linear programming problem graphically are explained. First step, formation of the linear programming problem. Formulation refers to translating the real world problem into a format of mathematical equations that represent the objective function and the constraint set. A proper perception of the question is needed for formulating it in a correct manner. Step 2, plotting the lines of the constraint on the graph. Constraint lines represents the scarcity of resources which are available. Generally, constraint lines are drawn by interconnecting the vertical and horizontal intercepts that are solved from each equation constraint. Step 3, determining the valid side of the constraint line. The easy way out would be to initiate with the plugging in of the origin coordinates, that is 0, 0, and analyze whether the constraint is satisfied. If it is the case, then all the points on the origin side of the line are feasible, that is valid, and all the points on the other side of the line are infeasible, that is invalid. If the constraint is not satisfied by 0, 0, then all the points on the other side and away from the origin are feasible, that is valid, and all the points on the origin side of the constraint line are infeasible, that is invalid. Step 4, identifying region of feasible solution. The feasible solution represents the area on the graph that is valid for all the constraints. Choosing any point in this area will result in a valid solution. Step 5, plotting the objective function to determine the direction of improvement. Betterment is along the direction of value which is greater when goal is maximization of objective function, and on the other hand, when the objective is minimization of the objective function, then betterment would be in the direction of value which is lesser for determination of the direction that is desirable to move along. objective function may or may not include feasible region. Step 6. Find the appropriate corner. Solutions which are optimal occur at corners. The corner which is more relevant, feasible solution region's last point touched by a line that is parallel to the two objective function lines. When more than one corner confirm the solution which is optimal, each corner and all the points along the line interlinking the corners confirm to the optimal solutions. Next, we will understand the linear programming problems through example. Let us consider an example, production of wooden tables and chairs. In this example, we will look at the profit maximization problem that a furniture manufacturer faces. The manufacturer uses wood and labor as inputs to produce tables and chairs as outputs. We consider that the manufacturer earns rupees 60 and rupees 80 for each unit of table and chair respectively. Also, the availability of wood is 3000 units and that of labor is 1100 units, and it takes 300 units of wood and 50 units of labor to make a table, and 200 units of wood and 100 units of labor to make a chair. The table depicts the relevant information for this linear programming problem. Step 1. Formation of the linear programming problem. With the help of the table, we will formulate the objective function. An objective function is developed in such a way that it is either maximized or minimized. In our example, the objective would be to maximize unit profit. Wood and labor row in the table is used to formulate the constraint line. We state the non-negativity conditions. Maximize z equals to 60x1 plus 80x2. This is the objective function where z is the profit. Subject to 300x1 plus 200x2 less than equal to 3000. This is the wood constraint. 50x1 plus 100x2 less than equal to 1100. This is the labor constraint. x1 and x2 both being greater than equal to 0. This is the non-negativity condition. Step 2. Plotting the constraint lines on the graph. We plot the number of tables on the x-axis and number of chairs on the y-axis. Next, we plot the constraint lines by finding the x and y intercepts for the two constraints equations. First, wood, that is 300x1 plus 200x2 less than equal to 3000. Now set x2 equals to 0 and solve for x1. This comes out to be 300x1 equals to 3000 and x1 equals to 10 tables. All wood is used to make the tables. Then 300x1 plus 200x2 less than equal to 3000. Now set x1 equals to 0 and solve for x2. So 200x2 equals to 3000 or x2 equals to 15 chairs. Here all wood is used to make the chairs. Labor. 50x1 plus 100x2 is less than equal to 1100. Now set x2 equals to 0 and solve for x1. We get 50x1 equals to 1100 or x1 equals to 22 tables. That is, all the wood is used to make the tables. 50x1 plus 100x2 is less than equal to 1100. Now set x1 equals to 0 and solve for x2. We get 100x2 equals to 1100 or x2 equals to 11 chairs. Here all the wood is used to make chairs. Now we plot the wood constraint line using the intercept x1 equals to 10 and x2 equals to 15 chairs, and the labor constraint line using the intercept x1 equals to 22 and x2 equals to 11 chairs. Step 3. Determining the valid side of the constraint line. Origin 00 is used to check the valid side for both the constraint lines, that is 300 multiplied by 0 plus 200 multiplied by 0 is less than equal to 3000 is valid. Therefore, the side of origin is the valid side of the wood constraint line. 50 multiplied by 0 plus 100 multiplied by 0 is less than equal to 1100 is valid. So the side of the origin is valid side of the labor constraint line. Arrows are marked in the figure indicating the valid side of each constraint line. It can be clearly seen from the figure. Step 4. Identification of the feasible solution region. The feasible region is the area on the valid side of both the constraint lines. Any point located on the invalid side of the constraint line is infeasible, and because of the non-negativity conditions, the feasible region is restricted to first positive quadrant. Step 5. Plotting the objective function to determine the direction of improvement. Now we will arbitrarily set profit z equals to 480 and z equals to 720, and then find x and y intercept and plot the two lines. Setting z equals to 480 first and x2 equals to 0. Now solving for x1, we get 60x1 equals to 480 or x1 equals to 8. Now setting x1 equals to 0 and solving for x2, we get 80x2 equals to 480 or x2 equals to 6. Next, setting z equals to 720 and x equals to 0 and solving for x1, we get 60x1 equals to 720 or x1 equals to 12. And now setting x1 equals to 0 and solving for x2, we get 80x2 equals to 720 or x2 equals to 9. Now we plot the objective function lines when z equals to 480 and z equals to 720 as shown in the figure. We can see from the figure that as we move away from the origin, z rises. Step 6. Finding the appropriate corner. Since we want to maximize z, we will draw a line parallel to the objective function lines that touches the last point in the feasible region while moving away from the origin. This identifies the most attractive corner, which gives us the amount of wood and labor that will result in the maximization profits, that is maximizing z. Thus, it represents optimal solution to the linear programming problem. It can be seen clearly from the figure. The most appropriate corner lies at the intersection of the wood and labor constraint lines. The intersection point of the two constraints is 4, 9. When we solve for z with this solution, we get z equals to 60 multiplied by 4 plus 80 multiplied by 9, which is equal to 960. Thus, the maximum profit of rupees 960 can be obtained by producing 4 tables and 9 chairs. Now, let us understand the limitation to the linear programming problems. Linear programming has turned out to be a highly useful tool of analysis. It is being increasingly made use of in the theory of firm, in managerial economics, in interregional trade, in general equilibrium analysis, in welfare economics, and in development planning. However, there are limitations and they are as discussed. First, linearity of relations. A primary requirement of linear programming is that the objective function and every other constraint must be linear. This means that inputs and outputs can be added, multiplied, and divided. However, in real life situations, several business and industrial problems are non-linear in nature. Second limitation is single objective. Linear programming takes into account a single objective only, that is profit maximization or cost minimization. However, in the present dynamic environment, there is no single universal objective. Third, it is complex to determine the particular objective function. Even if a particular objective function is laid down, it may not be so easy to find out various technological, financial, and other constraints which may be operative in pursuing the given objective. Fourth, given a specified objective and a set of constraints, it is feasible that the constraints may not be directly expressible as linear inequalities. Fifth, even if the above problems are surmounted, a major problem is one of the estimating relevant values of various constant coefficients that enter into a linear programming mode, that is, prices, etc. This technique presumes perfect competition in product and factor markets, but perfect competition is not a reality. Seventh, certainty. Linear programming assumes the values of the coefficients of decision variables are known with certainty. Due to this, linear programming cannot be applied to a wide variety of problems where values of the coefficients are probabilistic. For example, the linear programming technique is based on the hypothesis of constant returns. In reality, there are either diminishing or increasing returns, which a firm experiences in production. Eighth, constant parameters. Parameters appearing in the linear programming are assumed to be constant, but in practical situations it is not so. Ninth, it is a highly mathematical and complicated technique. The solution of a problem with linear programming requires the maximization or minimization of a clearly specified variable. The solution of a linear programming problem is also arrived at with such complicated method as the simplex method, which comprises of a huge number of mathematical calculations. 10th, largely linear programming models reflects trial and error solution, and it's hard to gauge solutions which are optimal to the variety complexities of economics. Now, we will summarize what we have learned in this module. We have learned that a linear equation, that is equation which is algebraic, the variable or variables quantities of which are the first powered only and the graph of which is made will give a straight line. Two approaches are commonly used to solve linear programming problems, that is graphical method and simplex method. Third, some of the limitations of linear programming problems are linearity of relations, single objective, complex to determine the particular objective function, certainty, constant parameters, highly mathematical and complicated techniques.